Okay, section 5.2. This is applications of right triangle trig that you learned in your geometry classes, but we'll add in all 6 trig functions. What you're supposed to learn in this section, this is just a screenshot from your e-textbook. You're supposed to learn how to use right triangles to evaluate trig functions, how to find function values for 30 degrees, which is the same as pi over 6, 45 degrees, which is the same as pi over 4, and 60 degrees, which is the same as pi over 3. You'll also recognize and use some fundamental identities. We'll speak of cofunctions and complements. We'll evaluate with a calculator, and then we'll solve some applied problems that use right triangle relationships. So, back to one of the memory devices you probably heard in high school, SOHCAHTOA, is just a way to remember the relationships for sine being the opposite over the hypotenuse, cosine being the adjacent over the hypotenuse, and tangent being the opposite over the adjacent. It goes for sine, cosine, and tangent. The other 3 trig functions are reciprocal relationships, and you can see that outlined at the bottom. So sine, opposite over hypotenuse. Its reciprocal relationship is cosecant, which is the reciprocal fraction, hypotenuse over opposite. You'll also notice those A, B, and C values. Don't worry about those. I'd rather you make sense of the actual lengths rather than more variables. Cosine, adjacent over hypotenuse. Its reciprocal relationship is with secant, which would switch to hypotenuse over adjacent. Tangent, adjacent, the opposite side over adjacent, with its reciprocal relationship, cotangent, adjacent over opposite. So these are the ratios that we use in order to work through problems with those. The ABCs that you see are in relationship to this, and just wanted to point out, so if I can zoom in just a little bit more, there we go, that when we name angles at the vertex, we use capital letters. For instance, this is angle A, angle B, and angle C. Those are capital letters. The lowercase letters are always opposite their corresponding angles. So lowercase a is the side that's opposite angle A. And lowercase b is the side that's opposite uppercase B. And lowercase c, and you have to be careful with this because they look similar, lowercase c is opposite angle C. Okay, we'll zoom back out. So how are these used, and what can we remember in order to go through these? That's what today's lesson is about. So if we remember labeling sides for trig ratios, sine, cosine, and tangent, this is that information that you saw just a moment ago. I'd like to play a brief video for you with that information.
In this activity, you will calculate the values of the 6 trigonometric functions of angle theta shown in the triangle. First, we need to calculate the value of b using the Pythagorean theorem. Substituting the values for c and a and simplifying produces the result. b equals 2 times the square root of 6. The value of sine theta equals the opposite side over the hypotenuse, which is 1/5. Cosine theta equals the adjacent side over the hypotenuse, which is 2 times the square root of 6 over 5. The value of tangent theta equals the opposite side over the adjacent side, or 1 over 2 times the square root of 6. Cosecant theta equals the hypotenuse over the opposite side, or 5 over 1, or 5. The value of secant theta equals the hypotenuse over the adjacent side, or 5 over 2 times the square root of 6. And the cotangent of theta equals the adjacent side over the opposite side, which is 2 times the square root of 6 over 1, or 2 times the square root of 6. Radical expressions are typically written without radicals in the denominators. We can simplify the values of tangent theta and secant theta by rationalizing the denominators to obtain square root of 6 over 12 for tangent theta and 5 times the square root of 6 over 12 for secant theta.
Okay, so let's put this to the test, and we'll work out the problem using example 2 from your textbook. I'm going to sketch this, and I recommend that you sketch this as we move along. My paper here to the side, and then we'll zoom back in on that paper. This is triangle ABC, and it's oriented with the right angle at the bottom right corner. We'd label it A, B, C. We know that side A, it has a length of 1, and that side C has a length of 3. We don't yet know side B, so that would be the first thing that we do. Notice that the solution tells you to begin by finding B, and since this is a right triangle, we know that the Pythagorean theorem works. So if I'm going to find B using Pythag, it would look like this. I'm going to switch the screens just a little bit. There we go. Sorry, having technical difficulties. So the Pythagorean theorem says the altitude plus the base squared will give us the hypotenuse squared. I know that the altitude is 1, so that's 1 squared. I do not know the base, that's b squared, and I do know the hypotenuse is 3 squared. 1 squared is 1, this remains b squared. 3 squared is 9, and then our goal is to solve for b. I will know I've finished when I have the term b isolated for the base of this triangle. First step would be to remove the 1 that's added to b. We do that by subtraction, so b squared is equal to 9 minus 1, which is 8. The next step would be to use the inverse operation and remove the exponent. The opposite of squaring a value is using the square root. So b is equal to plus or minus the square root of 8. We're not going to have a negative square root for trigonometry. These are real lengths, so we will use the principal square root of 8, which reduces to be 2 square roots of 2. And that's because this is the square root of 4 times the square root of 2. So now we know the base is 2 square roots of 2, and we can write each of our trig relationships based on that. The sine relationship is the opposite side over the hypotenuse, and we're looking for the sine of A in this case. So I circle A, and then everything that I do with this triangle now for sine is referring to angle A. So I need to know the side opposite angle A as well as the hypotenuse for the triangle ABC. The opposite side is 1. The hypotenuse for this triangle is 3. Therefore, the sine of A has a ratio of 1/3. You can get the cosecant of A just by doing the reciprocal function. Cosecant is the reciprocal of sine. So it's 3 over 1 or 3. These are cofunctions or reciprocal functions. Okay, we'll repeat the process, and this time we'll do cosine. The cosine of A would be the adjacent side over the hypotenuse. Side B is the adjacent side. It was 2 square roots of 2. And the hypotenuse for this triangle is still 3. So the cosine value ratio is 2 square roots of 2 over 3. Its reciprocal would be secant. The secant of A is the reciprocal h over A, or hypotenuse over the adjacent side, which is 3 over 2 square roots of 2. We do need these to be rationalized. You can use your calculator if it has that possibility. If not, then this is the simplification part. You're not allowed to have a radical value in the denominator for rational numbers. It needs to be a whole number or an integer. So in order to remove the square root, we multiply top and bottom by the irrational part. This part is called rationalize. You're rationalizing the denominator, turning it into a rational number. When you multiply across, you get 3 times the square root of 2. On the bottom you have the whole number 2, now times the square root of 4, because 2 times 2 is 4. 4 has a square root, so now we have 3 square roots of 2 over 2 times 2, or 3 square roots of 2 over 4. Therefore, the secant value is 3 square roots of 2 over 4. Okay, let's slide up just a little bit. We've done sine, we've done cosine. The last one of these to refer to is tangent. So tangent of A is the opposite side over the adjacent side. The opposite side was 1. The adjacent side was 2 square roots of 2. Okay, this one will need to be rationalized as well, so it's that same process you see just above it. The irrational part is the square root of 2, so we'll multiply top and bottom by the square root of 2. This works out to be the square root of 2 over 2 square roots of 4, which is the square root of 2 over 2 times 2, which is 4. The cotangent of A is the adjacent over the opposite, so it's 2 square roots of 2 over 1, which is just 2 square roots of 2. Okay, so back to, we've completed that for sine, cosine, and tangent. Here's one for you to try. Let's do this one that's in the middle. You can pause your feed, get it set up. So we're going to focus on this one that's in the middle, and our reference for this will be to label our triangle with angles A, B, and C, and then we're going to do our trig ratios for angle B this time instead of angle C. You'll see that I've sketched that out, and I have labeled everything except C. I wanted to talk to you just for a moment about how I knew what to put where. I was given side A, side B, and side C. Angle A is opposite side A. Angle B is opposite side B. That means that angle C is opposite side C. In all of these ratios, I've asked you to find sine, cosine, and tangent based on angle B. So let me circle angle B. And everything that I do for this problem will be in reference to B. So this one is the opposite side, this one is the adjacent side, and this one is the hypotenuse. In order for this to work, I do need side lengths for A, B, and C, and I am missing side A. So just like in the other problem, use that Pythagorean theorem to locate side A. A squared plus B squared equals C squared. That means that A squared plus 4 squared is equal to 5 squared, or A squared plus 16 equals 25. Collect your constants together. Isolate the variable. A squared is equal to 25 minus 16, which is 9. Still trying to isolate that A, take the square root. We're only using principal square roots because these are distance. So A is equal to the square root of 9, which is 3. Now we know the opposite, the adjacent, and the hypotenuse. We're ready to put in our information. So for sine, sine is opposite over the hypotenuse. The opposite side is 4. The hypotenuse is 5. We have the sine of B as 4/5 ratio. The cosecant of B is the reciprocal relationship. It's hypotenuse over opposite, or 5 over 4. We can repeat the process for cosine, this time looking for the adjacent side over the hypotenuse. The adjacent side is 3, the hypotenuse is still 5, so 3/5 is the cosine ratio for B. Secant is hypotenuse over adjacent, or the reciprocal, which is 5 over 3. The last ratio is tangent. Tangent is opposite over adjacent. The opposite side was 4. The adjacent side was 3. So 4 to 3. And notice that that is the numerator for sine and cosine. We'll talk about that a little bit later. And then cotangent is the adjacent side over the opposite side. It is the reciprocal for tangent, so 3 over 4. All of these were whole numbers. Everything's rational, no rationalizations necessary. As we move through and work on right triangle trigonometry, there are two special right triangles that you visited in geometry that will come back to play within the unit circle. And these two are the isosceles right triangles that have two 45-degree angles, and their legs are always 1 unit and 1 unit in a unit circle. A squared plus b squared equals c squared. The square root of 2 is always the hypotenuse. The other is the 30, 60, 90 special triangle, where you have the hypotenuse is always twice the short leg, and the long leg is the short leg times the square root of 3. So it looks like if the short leg is 1, the long leg is 2, and, the hypotenuse is 2, and this is the square root of 3. We will go through some examples and reminders of how these work in just a moment so that you'll be able to apply them within the unit circle. So here's a special right triangle with an angle of 45 degrees. Take yourself a moment and jot this particular problem down, and then we'll work through it together. We will label all of our angles and all of our sides, and then we will find the 6 trig functions for this triangle. Remember that you can pause the recording at any time for this. So let me zoom in on my paper. I've made myself a diagram of this problem. I know that this base length is 5 and that this angle is 45. If you recall, the triangle sum theorem says that any triangle has 180 degrees as a maximum measure of degrees. This is 90 and this is 45. In order to total 180 degrees, this angle would also have to be 45. There's also a theorem that you used in geometry that says if your base angles are congruent, if this is an isosceles triangle, then the sides must be congruent, because isosceles means that you have two sides congruent. So I know that this base is congruent to this base. If this one's 5, this one is also 5. And then you can use the Pythagorean theorem, or you can remember that this should be times the square root of 2. I recommend that you try a few of these to see why this works. So the hypotenuse here would be, let's work our problem out here, 5 squared plus 5 squared would equal c squared. 25 plus 25 would equal c squared. 50 would equal c squared. Take the square root of both sides. The square root of 50 would equal c squared. That breaks down into be 25 times 2, so the square root of 25 is 5. 2 doesn't have a square root, it becomes the square root of 2. This is 5 square roots of 2. And for any isosceles right triangle, this will be true. If the legs are 5, the hypotenuse is 5 times the square root of 2. Just a real quick shortcut for that. Now, if we're looking to find sine, cosine, and tangent, we need to define what we're looking for. Let's let this be angle B, this be angle A, angle B, and angle C. C should also always be adjacent to the opposite to the hypotenuse. Let's find sine, cosine, and tangent for angle A. You can pause the video, try that problem, and then come back to see how we've done. How'd you do? Okay, moving back. This time we're given a special right triangle that has a 60-degree angle. We know that all angles total to be 180 degrees, so if this is 60 plus 90, that would be 150. That means that the missing angle must be 30. Pause your video for a moment and jot down this part, and then there's a reminder that the short leg would always be opposite the smaller angle, so it's a good reference for us as we go. Again, take a moment, pause your video, jot that information down. Okay, I've jotted this down on my paper. It looks something like this, with a side length here of 4, an angle measure here of 60, an angle measure there of 90. 90 plus 60 is 150. 180 degrees minus 150 degrees would mean that this angle must be 30. And I know that this is the short leg because this is the smaller angle. The long leg, let me label that, the short leg. Do a real quick geometry lesson. The long leg would be opposite the larger of the angles. So this is the longer leg. And the nice thing about this special right triangle is that the longer leg is always the short leg times the square root of 3. So this would be 4 square roots of 3. The hypotenuse, which is always opposite the 90-degree angle, is the short leg times 2. So this would be 2 times 4, or 8. Now we have all 3 sides labeled and we have all 3 angles labeled. What we haven't specified is what function are we looking for and which part are we doing. So I want to do the sine of 30 degrees, which means that my reference will be this 30-degree angle, and everything that I do is in reference to it. Sine is still the opposite side over the hypotenuse. Opposite 30 degrees is 4. The hypotenuse we found to be 8. And it turns out if you tried your calculator and it's in degree mode, the sine of 30 degrees is actually 1/2 or 0.5. I could show you that demonstration if I could find my calculator. Here it is. So this is just the basic calculator that I use. I make sure that I am in degree mode. So I am now in degree mode. I can do the second quit. And I could try just the sine of 30 degrees to see if it gives me the 1/2. Sure enough, there it is, 1/2. If you have a calculator that doesn't use fractions, you'll probably see it 0.5, but you know that that is 1/2. Just a quick tutorial. Then if I wanted to find the cosecant of 30 degrees, I could use the reciprocal relationship that it would be 8/4 or 2/1. If I'm looking for the cosine of 30 degrees, I repeat the process, but I'm looking for adjacent over hypotenuse. The adjacent is the one that touches it. This is the adjacent leg to 30 degrees. Its length is 4 square roots of 3. The hypotenuse is still 8. This reduces because 4 and 8 have a common factor of 4. 4 goes into 4 one time and you're left with the square root of 3. 4 goes into 8 2 times, so the cosine of 30 degrees is always the square root of 3/2. And if you wanted to try that with your calculator, you could try cosine of 30 degrees to see what it does for you. And sure enough, there it is, the square root of 3/2. In order to do its reciprocal, you need secant of 30 degrees, which is the reciprocal of this one. It would be 8/4 square roots of 3. The 8 and the 4 would still reduce. 2 and the square root of 3, but this one would need to be rationalized. The irrational part is the square root of 3. You multiply top and bottom by the square root of 3 to rationalize. It's 2 square roots of 3 over the square root of 9, which is 3. So there is the secant of 30 degrees. So we've done the sine of 30 and its reciprocal function, the cosine of 30 and its reciprocal function. Now we'll do the tangent of 30, and I'm running out of room, and its reciprocal function. So the tan of 30 degrees, and we know 30 degrees is in our unit circle as well, so all these things hold true. Tan of 30 degrees is the opposite side over the adjacent side. The opposite side of 30 was 4. The adjacent side is 4 square roots of 3. Yes, this reduces because 4 and 4 have the common factor of 4. 4 goes into 4 one time. 4 goes into 4 one time, and you have that remainder of the square root of 3. But you will need to rationalize. Again, if your calculator doesn't do it, you look at the irrational value and you multiply top and bottom to keep this balanced to get the square root of 3 over the square root of 9, which is 3. And then you can do that reciprocal function for tangent. So cotangent of 30 degrees would be 4 square roots of 3/4. The 4's would cancel and you are left with the square root of 3. So I hope that helps with that special right triangle information. Here are some notes for you on the reciprocal identities. We've discussed these, that sine is the reciprocal of cosecant. So cosecant is 1/sine and sine is 1/cosecant. If you need to jot that information down, go ahead, pause your video, write down anything you need to, and then we will begin working through example 5. While you're writing it down, I'm also writing it down. So here's example 5, and it says using the quotient and the reciprocal identities. You will be very familiar with the reciprocal identities before chapter 5 is finished. They are used so many times they become second nature. We'll be using the quotient and reciprocal identities to help us out with this information to work through example 5. Given the sine of theta is 2/5 and the cosine of theta is the square root of 21/5, find the value of each of the remaining trig functions. I wrote that information down over here, and there's several different ways to work the problem. Here's my recommendation that we keep these in some sort of order so that we can compare the original trig functions easily to their reciprocal identity functions, cosecant, secant, and cotangent. We remember those relationships for sine. Sine is always the opposite over the hypotenuse. Now for this one we're given that the sine ratio is 2/5. That means that the opposite side is 2 and that the hypotenuse is 5. And if you wanted to draw yourself a right triangle, here's theta, the opposite side is 2 and the hypotenuse is 5. We're given that information. This being the angle theta. Well, like any other right triangle, we would need to know the third side or the adjacent side. This is opposite. This is hypotenuse. I am looking for the base of this triangle, so I'm looking really for side B. It's the Pythagorean theorem. It's a squared plus b squared equals c squared. Just like all of those are. You can go out to the side and work that information so that you can get the base, which is the adjacent side. I'm going to work it right up here. So if a squared plus b squared equals c squared, I know that a, the altitude, is 2 squared. I do not know the base, so that's b squared. I do know the hypotenuse is c squared, and it's 5. This means that 4 plus b squared equals 5, 25, and b would be 25 minus, so it's the square root of 21. That's where this value came from. So the adjacent side is the square root of 21, just exactly like they told us in this original problem, the square root of 21/5. That is the adjacent side and the hypotenuse. So there's the background work. That's how they knew what this was based on sine. Now you can use your information to find the rest of them. That was adjacent over hypotenuse. Tangent is opposite over adjacent, so the opposite side is 2. The adjacent is the square root of 21. That's not rationalized. It becomes 2 square roots of 21/21. These are all reciprocal relationships, which means I can just invert the fraction. Cosecant would be 5/2. Secant would be 5 over the square root of 21. Make sure you rationalize. It becomes 5 square roots of 21/21. And then the cotangent will be the reciprocal of tangent, which would be, let's start with the original one, square root of 21/2. So we worked that one out. You can pause, go back, look at it again. Here are the Pythagorean identities. You can pause your recording to take a look at those. Sine squared plus cosine squared is always 1. That's because a squared plus b squared equals 1. 1 is the radius in a unit circle, so all those values have to be 1. 1 plus tan squared is secant squared in a unit circle, and 1 plus cotan squared is always cosecant squared in a unit circle. These are Pythagorean identities because a squared plus b squared equals c squared in any right triangle. Example 6. It says use a Pythagorean identity. Those are the ones that you see. Given that sine of theta equals 3/5 and theta is acute. Find cosine of theta. Okay, it gives me sine. I'm looking for cosine. This is the Pythagorean identity that has both sine and cosine. Sine squared plus cosine squared equals 1. I will use that identity to locate cosine, the value of cosine, and it looks like this. Sine squared of theta plus cosine squared of theta equals 1. They give me sine. I can substitute what I know and solve for what I do not know. So 3/5 squared, I don't know cosine, plus cosine squared theta equals 1. Just like solving for any other equation, you have to isolate what we're looking for, and we are looking for the cosine of theta. 3 squared is 9, 5 squared is 25, plus cosine squared theta equals 1. The next step would be to subtract 9/25 from 1. So cosine squared theta equals 16 over 25. Use your calculator or a common denominator. And then to undo the square, you take the square root. So the cosine of theta would be the square root of 16. Let's move it over here. The cosine of theta is the square root of 16, which is 4, and the square root of 25, which is 5. So we just found the cosine of theta. Here are the cofunction identities. The chart is here. Sine is cosine. You start with 90 degrees and you subtract whatever angle. These are cofunction, and the word complementary angles mean the same. If you go back to your geometry days, a complementary angle was one that added to be 90 degrees. So you are looking to see what its complement is in order to know the cofunction. So sine's complement or cofunction is cosine. You take what you're given, subtract it from 90 degrees. Cosine's the other way around. You start with sine and subtract it from 90 degrees. If you are dealing with radians, instead of using 90 degrees, you just use its equivalent, pi over 2. Pause your recording, write down your cofunction identities, and then we'll be working through example 7 together. And then welcome back. The directions for example 7 are to find a cofunction that has the same value as the sine of 72 degrees. I know, referencing my cofunction chart, that is sine of theta is equal to cosine of theta, 90 degrees minus your angle. So I can say that sine of my 72 degrees is the same thing as cosine of 90 minus 72. That means that that's the cosine of 18 degrees. Has the same measure as the sine of 72. And you can prove it to yourself using your calculator, making sure that you're in degree mode. You can type in sine of 72. Turn your calculator on first. Sine of 72. You'll see its value. And then the cosine of 18 degrees. And you'll see its value. They're the same. So you've just proven that that cofunction identity part works. Now let's look at cosecant of pi over 3. So if you haven't already written that one down, let's do it. Cosecant of pi over 3. I know from my formula that the cosecant of theta is equal to the secant of 90 minus theta, but since this is in radians, we'll do the secant of pi over 2 minus theta. Okay, so I've written that information down. This is in radians, therefore I had to make sure I use the pi over 2 value. This means that the cosecant of pi over 3 is equal to the secant of pi over 2 minus pi over 3, which equals the secant of, you could use a common denominator, which would be pi over 6. So the first one would be 3 pi over 6, and the second would be 2 pi over 6. And you subtract and you get pi over 6. So welcome back. We'll be looking at some application problems. Before we look at those application problems, let's go back and just get you some basic notes for these. Get to see everything that I have opened on my screen, which is a lot. Bear with me. Here's what I need. You may want to take a screenshot of this and save it. That's probably the easiest thing to do. But there's always questions when we're dealing with right triangle trigonometry about a point of view and how to measure an angle of elevation and angle of depression. Notice that this has three vertices of the triangle. One where the observer, that might be your point of view, is. Another at an airplane that's taken off. And then another with a car that's moving away from this building. Everything is based on the observer's point of view. So there's an imaginary horizontal plane here, and things that above their horizontal point of view would be considered an angle of elevation. That's the line of sight of the observer. Or if the observer's looking down, the line of sight is below. Not all application problems deal with angles of elevation and depression, but if they do, here's an excellent resource. I just screenshot this from your e-textbook. You can screenshot it from this recording now and save it in a Word document if you like. We are going to move in and work 2 or 3 application problems that deal with right triangles. So let's get started. So here's my first one. It says to find the distance across a lake, a surveyor took the measurements in that figure that's shown, and to use the measurements to determine how far it is across the lake. The lake has sort of been highlighted in blue, and we're trying to find the length of the hypotenuse that's here. In order to work that, we label our triangle A, B, and C such that they did. We put in our angle, that was 42 degrees from this position. I know that the distance from A to C is 50 yards. I can find the distance A if I can figure out what the relationships with sine, cosine, and tangent are here. So this is how trigonometry is used. If this is angle A, the side across from it is called the opposite side. This side would be called the hypotenuse. And this side would be called the adjacent side. Everything based on that 42-degree angle. It is the distance from B to C that they ask for, though they just as easily could have asked for the distance from A to B. If we're looking at A to C, A is opposite and they give me the adjacent. If I am looking for the opposite and I'm given the adjacent, that's the tangent function. So I'm looking for the tan of 42 degrees is equal to the opposite side I do not know. We're using the variable A for this one. And the adjacent side they gave me in this problem is 570 yards. We'll put that in here. In order to solve this, cross multiply. 1 times A is A. Don't type anything in your calculator yet. Go ahead and write down your step. This is 570 yards. We'll just do 570 times the tan of 42 degrees. Now you're ready to grab your calculator. I don't expect you to have memorized the tangent of 42 degrees. If I were you, I would clear out anything that I've been doing, especially if you're working with either degrees or radians and back and forth. This is in degrees. Make sure my calculator is in degrees. And then you can type in 570 tan 42 degrees. Close the parentheses, press equals, and you'll find out that's about 513.2 yards. Another look. We were looking for the opposite. We were given the adjacent. That ratio for opposite and adjacent is tangent. So we did the tan of our angle 42 degrees is equal to the opposite side A over the adjacent side 570. Cross multiply. 1 times A is A. 570 times the tan of 42 works out to be approximately 513.2 yards. Second problem I'd like to look at. We're looking at a telephone pole that's shown here. We have a telephone pole, probably called a power pole now because we don't use landline phones. They have a guy wire. The guy wire or guide wire is the one that attaches it to the ground so that the telephone pole or the power pole stays at a 90-degree angle with the ground. They give us information that the guy wire is 76 feet long. That's labeled as 76. They give us information that the telephone pole is 60 feet tall. And on this one, they ask us to find theta. We are looking for this particular angle in theta. It is a right triangle because the ground and the pole should be at a 90-degree angle. So we'll sketch out this problem, and let me show you how to use trigonometry to find an angle. You can pause the video if you need to. So I'm looking at a telephone pole, the ground, and a guy wire. This is the wire. Is 76 feet. This is the telephone pole or the power pole. It is 60 feet. We know that this is a right triangle because in order for this to stand properly and to support its wires, it must be at a 90-degree angle. And the problem asks us to figure out what is that angle. We'll use trigonometry to do it. Based on this angle, this is the adjacent side and this is the hypotenuse. The trigonometric function that deals with adjacent and hypotenuse is cosine. So we know that the cosine of theta is equal to the adjacent side, that's 60, over the hypotenuse, which is 76. So we have our problem set up as cosine of theta equals 60 over 76. We'll know we have a problem worked when we have that theta term, which stands for the angle, isolated. We haven't talked yet in this class about how you undo cosine, but it's called arc cosine, and it looks like cosine to the -1 power on your calculator to find an angle. So here are the keystrokes to do that. With your calculator, you're again making sure you are in degree mode. To undo cosine, I do cosine -1 or arc cosine of 60 over 76. Type that in your calculator. My calculator, I just hit cosine twice and it gives me that value. This is a fraction, 60 over 76. This will give me my angle and I'll round it to the nearest degree. So this is about 37.8 or 38 degrees. And we could label this at the top. Once you know that angle, you can subtract from 180 to find the angle it's formed at the ground as well, if you liked. And we'll go ahead and do that just for the part. If we are asked for this angle, it'd be 180 minus 90 minus the 35. 90 minus 35, I believe that's 55. And now we know all of the angles, and you could use Pythagorean theorem even to find that length from the end of the guy wire to this part, if you were asked to do so.